Right, by the very definition of the upper and lower integrals, we know that there exist subdivisions which approximate the upper and for which the sums approximate the integrals as well as you want. And if you start with some subdivision, you can get better subdivisions, they get better approximations by subdividing, by refining them. But is there like some numerical measure you can take? And maybe you kind of believe one. Let's talk about diameter of sets and fineness of meshes. So, right here. The diameter of a set J, I'll denote it as diam of J. Well, you know what that should mean. That should mean like, take the 2 points in the set that are farthest apart and measure the distance between them. But maybe there aren't 2 points in the set that are maximally far apart. Maybe you need to take a supremum instead. So the diameter of any set is the supremum of the distance from x to y, where x and y are in that set. Oh, Christ. The name of the set is J. Now, let's think about subdivision and like even the philosophy of Riemann integration. So if you want to integrate something over the shape some function, the way you would want to do it, you want to break it into like a bunch of really, really little pieces. So like, that probably wouldn't be good because it has like one really big piece. So you really want to break it up into a bunch of pieces that are all uniformly little. So the next thing I'm going to define is a measure of that littleness. Let x be a figure and delta be a subdivision of x into figures. Then the fineness of x, I'll use that word. How fine x is the largest diameter of all of the sets in the subdivision. That makes sense, right? If you want all of the pieces to be little, you just want to make the biggest piece little. That would do the trick. And maybe just for the sake of being explicit, here is a circle of radius 3 centered at 0. Here is a subdivision of it by taking a bunch of 1 by 1 squares and intersecting that with the circle. That is a subdivision, right? Each of the pieces is a figure because it's an intersection of a circle, which is a figure, and a square, which is a figure. So this is a subdivision. What is the fineness of that subdivision?
We define the difference in like points by like L2 north, right?
Yep.
Okay.
I'm hearing a few root 2s, right? As you would say, well, grab this particular piece. It's got one side length 1, one side length 1. It looks like that length is the square root of 2, and those are the 2 farthest apart points in that square. Cool. So here is the main result of today. Let's replace that with today's. It just says that if you want to integrate a function over a figure, you can approximate the integral as well as you want just by making the subdivisions fine. Let x be a figure, let f from x to where be a bounded function. Then for any epsilon bigger than 0, there exists a positive number delta bigger than 0, such that if capital delta is a subdivision of x, so that the fineness of that subdivision is less than that positive number delta, then the difference between the lower integral and the lower Darboux sum is less than epsilon, and the difference between the upper integral and the upper Darboux sum is less than epsilon. Nice. So does the statement make sense? Let's try to prove it. So I guess if like this stuff about how delta is being chosen can you just find a subdivision delta which satisfies those two inequalities? What's the definition of this? How do we define the upper Darboux integral?
Is that the infimum of all the s pluses?
Yeah. Nice. So if this is the infimum of a set, can you find a thing in that set that's as close to the infimum as you want? Right, that's the definition of infimum, right? The infimum is a lower bound so that there's stuff in the set arbitrarily close to that lower bound. And that's what I'll do first. I'll get this starting subdivision. Let x be a figure, let f from x squared be a bounded function. F is bounded, so is the absolute value of f. We'll see why that's relevant later on. Let m be an upper bound. Next, I need to prove something for any epsilon bigger than 0, so I better consider any epsilon. Then there exists a subdivision. I'll call it delta 0 because it's like a starting subdivision. It's not the one that I want. For which the upper and lower Darboux sums are within an epsilon of the upper and lower Darboux integrals. So I can get those differences to be as small as they want. And you know what, I'll put an epsilon there for now, although I'll tell you that I'm going to offset them because it's going to be epsilon divided by something. And we'll figure out what we need to divide by. Nice, well, what's the difference between that delta 0 and what we want to prove? Let's even just think about quantifiers. How is that delta 0 quantified right now? It exists, and that's it? Like I just have one. How is the delta in the theorem statement quantified?
That's fineness is less than delta.
Yeah, but it's every subdivision whose fineness is less than delta. So there are lots of problems with just saying I'm done at this point. This delta 0 is just a single example I need to prove on for every subdivision. I have no idea what the fineness of this subdivision is. But that's a starting point anyway. And so, let's see, how many people actually turned in the homework that was due today? All right, well, here's a result that's in the homework, which maybe I'll even be happy to like pause and talk about. Let's consider any I in delta 0. So this is a subdivision into figure, so each I is a figure. One of your homework problems was to prove that there exists some positive quantity, delta. It's dependent on this choice of big I, so I'll call it delta sub I. And a figure I prime contained in I, so that for every point y in I prime, the ball centered at y of radius delta is contained in I. And the difference between the volume of I and the volume of I prime is as small as we want it to be. So this will be a different epsilon, so I'll try to color code it. This one will be red. It'll be epsilon eventually divided by something. How many people made it to even making progress on this homework problem? Okay, let's talk about it. Well, Dan, I know that you didn't because you haven't been here for the past week and you're not in the class. So let's talk about this particular problem. And you know what? Maybe I'll even go ahead and say, let's put today's lecture even on hold for a bit. Let's just talk about that exercise, that the theorem that's alluded to right there. So let's try to do it. Yeah, there's some scratch reviews. So here's the theorem. Well, it's called I called it I in there, but right now maybe, I don't know, what's a good name for a figure right now? X, okay. Let X be a figure. That's what I've used a lot. I wasn't sure whether you guys would want to use that letter because that's also like the X that's in the theorem that we're trying to prove right now. Let X be a figure. Then there exists some other figure, X prime contained in X, such that then there exists a for every epsilon bigger than 0, there exists a delta bigger than 0, and a figure J, no, X prime, contained in X, such that the volume of X minus X prime is less than epsilon, and for every X in X prime, the ball is centered at X of radius delta is contained in X. So let's just draw a picture of what this is even saying. So this is saying that if you draw a figure, then you can find a subfigure of this figure, which only misses a very little bit of the volume of the figure, and has the property that whenever you take a point in the littler shape, it's like a distance delta away from not being an X anymore. So, like, you can draw a picture of what this is trying to do, right? Like, there's the idea of what this is saying. What's the volume of the difference between the black shape and the white shape? Is it little? By taking the red card like really close to the black card, you can make it really, really little. If you take any point in the red thing, is that point in the red thing a positive distance from everything that's not in the black thing? Yeah. So that's what the theorem is saying. Let's try to prove it. And first, I'll suggest trying to prove it if X is a rectangle. So let's see. Proof if X equals a product of a bunch of AI minus B, BI comma AIs. So let's do it. So let's take that as X. Let's let epsilon be bigger than 0. And well, let's try to draw a picture of how this will go. So let's see, so there's like A1 to B1 cross A2 to B2. I can't draw more dimensions than that on a piece of paper. So that's as high as I'll go. How could you draw a figure that almost fills up that green rectangle but has what is totally interior to it?
You have to be going from A1 plus epsilon to B1 minus epsilon.
Yeah, I won't use epsilon. This will be the job of the delta.
Delta.
Yeah, so if there's A1 plus delta, B1 minus delta, and the same thing vertically.
Yeah.
So let's let X prime be the product of a bunch of BI minus AI plus deltas to BI minus deltas. Where I get to choose what delta is, right? Well, delta is something that I get. So let's just do a quick check. What's the volume of X? How do you compute the volume of a rectangle? Well, let's write it this way. What's the volume of a volume of a rectangle? What's the volume of that green rectangle?
B1 minus A1 times B2 minus 2.
Yeah. And then it's the same thing for a product, right? Similarly, can you compute the volume of the right rectangle? I won't even bother writing those down because I just want to talk about it a little bit more. What's the limit of the volume of all the right rectangles as delta goes to 0? Volume of the bigger rectangle. From that, well, I mean, you could come up with an explicit choice of delta, but just out of that limiting statement, could you conclude that there exists a positive number delta such that this quantity is less than epsilon? So there's your choice of delta. If you take any point in this right rectangle, does it follow that the ball centered at that point of radius delta is contained in the green rectangle? I think so. So there's the proof. All right, it's not all written, but that's why it's also homework. Now let's try to do it if we have an actual, like just an arbitrary figure. So let's take x to be a figure. Can you approximate the volume of a figure by using only rectangles that are totally contained in that figure? Yeah, that's like the definition of a figure, right? You can always compute the inner volume as a limit of a, you can always approximate the inner volume by using inner rectangles, but if the inner volume is just the volume, use those rectangles. So let's let R be a bounding rectangle and delta be a subdivision of this rectangle R. So there's the picture of the bounding rectangle. There's the figure x chosen such that the inner volume of x minus the inner volume, well, that's just the volume of all of the inner rectangles is less than, well, let's say epsilon over 2. Maybe that's not what I want. Maybe it is. Let's draw a picture of that. There's a picture. Let's focus in on, oh, the color coding is going to go to shit. That's okay. Let's look at that particular inner rectangle. Could I find a smaller rectangle contained in that rectangle, which has almost all of the volume of the blue rectangle, but for which there exists a delta so that that whole rectangle is contained in the blue rectangle? Yeah, that's exactly what the first thing that the proof has been sketched for. I don't know, let's call that lemma A. So for each I in Everyone feel pretty okay right now? Oh, well, neat. Let's see if we've just done the job. So let's take x prime to be the union of all of these I primes. let's see if this works out. Is this x prime automatically a subset of x?
Could you repeat that?
Yeah, so this set x, so I need to set x prime. If you look at the statement on the very top, x prime needs to be a subset of x. Is this set x prime a subset of x? Yeah, because each of these I primes is contained in I, which is contained in x. If I take a small ball, so each of these I primes comes with delta I. So that if I take a small ball of radius delta I centered at a point in I prime, that whole ball is contained in I? Does it follow that that whole ball is contained in x? So I think if I take the smallest of all of the deltas, and now let's see. If I take the volume of I prime, that's really close to the volume of I. That's like one of those things that we proved in that lemma. And they're only finitely many. So I think if I take all of those I primes, where number means number of things in a set. I don't want to use like vertical bars because that's like the mesh size of delta right now. Oh, cool. So that means that the difference between the inner volume of x, that's the sum of a bunch of volumes of rectangles, and the volume of this, well, that's literally just a union of a bunch of disjoint rectangles. So its volume is a sum of a bunch of volumes of rectangles. So the volume of x prime is really close to the volume of x, well, delta. The volume of x is really close to the inner volume of x, well, delta. Does that mean that the volume of x is really close to the volume of x prime? Yeah, so there's the proof. So you guys now have the task of writing that as a coherent proof as opposed to like the gibberish that I just said. And I feel okay doing that. I think like Ava's given out some homeworks like that where he'll explain the proof and then the students have to write up the proof.
Yeah.
I like that idea. And this is like a much harder version of that, right? Because this is actually like a hard result. I think, does Ava usually do it for results which should be easy?
Mm-hmm.
Okay. So you guys have some thinking to do about putting this together. But does the idea of that make sense? Hopefully, especially to those of you who have spent some time thinking about the problem. Cool. And I guess maybe it's convenient that this is now all videographed and will show up on the YouTube. Of course, maybe this is like a play to just get my YouTube video hits up.
The unlisted YouTube videos.
Yeah, unlisted YouTube videos with. Right, the maximum number that I would maybe expect would be like 6. Not counting when I click on it to check if it has successfully uploaded. I said maximum. It's an upper bound. Yeah, maybe maximum is it's an upper bound. So now that we've like sketched the proof of that result, let's use it. So for this subdivision, for each element of this subdivision of the figure into smaller figures, which is drawn right there, I'll break each one of those figures up into a smaller figure paired with a positive number delta. So, I mean, I'll really draw them all right there, but so if there's one of these i's, then I prime is contained in I. The difference between the volume of I and the volume of I prime is as small as I want to make it. And, well, if I draw the little circles, well, let's draw the little circles. For every point in I prime, there's a fixed, constant, positive number, so that the whole ball centered at any point inside of the green rectangle is contained in that black rectangle. Though that black rectangle is really just a figure. So I'm just going to go to the left and draw also the same things on these blown up ones. So here's one of the choices of I. And there's the choice of I prime. Everyone feel pretty okay? And shoot, let's just draw all of them. There's another one of the I primes for a different choice of I. There's another one. And that last one's really little. In fact, do you think if that epsilon is chosen to be big enough, some of those I primes might just be empty? But if epsilon was, say, if the positive number I chose were bigger than the volume of that little corner piece, then I wouldn't need to take any of that little corner piece. I could just take the empty set and be satisfied. Nice. So there's a picture of all of these. I'll set x double prime. So let's see, I'll set I double prime to be I minus I prime. Oh, you want to scroll it down. I'll set I double prime to be the difference between I and I prime. So if you like, that's like the stuff that I'm forgetting about. So there's I double prime. And I'll set x double prime to be the union of all of those defects. So in this picture, there's the bit that I'll call x double prime. Let's compute the volume of x double prime. So let's see. So are all of these I double primes necessarily disjoint? No. Well, each I double prime is certainly contained in an I. Are all of the I's necessarily disjoint? Because this is a subdivision? Well, not necessarily, but they have zero volume in their intersection. But that's as good as being disjoint if we just want to compute the volume. So all of these I double primes have no volume in their intersection. So the volume of x double prime is just given by the sum of all of the volume of I double primes, which is the sum of the volumes of all of the I minus I primes, which in turn I have I left out the V for volume. Let's do one more step. That's equal to the sum of all the volumes of the i's minus the volumes of the I double primes. But each of these blue sets, each of these blue quantities is less than epsilon? Yeah.
And that second volume on the right, on the last equal, should that be an I double prime or an I prime?
Better be an I prime. Thank you. So this right now I've arranged to be less than the red epsilon. So that x double prime I've arranged to have arbitrarily small volume, but again that epsilon, the red epsilon, is eventually going to, well, no. Epsilon times the number of things in delta 0. Because, right, how many terms are in that sum? There's one for each thing in delta 0, and each of those terms is less than epsilon. Nice. Where the number of things in delta 0 indicates the number of elements in delta 0. And so now, well, each of the i's have gotten a different choice of delta. And so even if you don't know how the proof is going to go, you know what you should do whenever you see a bunch of different positive deltas and you need to use all of them. You should just take the smallest one. And they're only finitely many, so you can take the min and not the in. So it's that delta, the min of all these delta i's such that I is in delta 0. Nice. So there's my choice of delta. Let's go back to the actual theorem statement. Maybe I'll even write the theorem statement on the board. So what was it? It was for every epsilon bigger than 0, there exists a delta bigger than 0 such that for every subdivision, capital delta of x, if the fineness of that subdivision is less than delta, if the mesh size is less than delta, then here's my goal. So one of the things I needed to do was declare an epsilon. Nope, I needed to find the delta, and I just did. I now need to prove something for every subdivision delta of x, which satisfies this hypothesis. So let's consider any such thing. Consider any subdivision delta with mesh size less than delta. What is it that I need to show? I need to show that the difference between the lower integral of over x of f dv minus s minus of f using the subdivision delta is less than epsilon. And let's try to motivate a little bit. Do I already have a subdivision which satisfies that conclusion? Yeah, like this delta 0 that I started with. So what I'll kind of try to do is I'll try to show that this lower Darboux sum is pretty close to being the lower Darboux sum corresponding to that delta 0 that we started with, because then up to deciding maybe some epsilon should be epsilons over 2's. So here's how I'll do it. Instead of trying to directly compare this delta and the delta 0, well, when you have two different subdivisions, how can you get a new subdivision which does a pretty good job at understanding both of them? Refinement. Get a common refinement. So let's let delta prime be, I'm calling it the standard common refinement. What are the elements of this? If I asked you to find a refinement of two different subdivisions, how do you do that?
You intersect their elements.
Intersect their elements. So let's take delta prime to be the set of, well, let's see, set of all things. I'll index it by an I in delta 0 and a j in delta. It's things that look like I intersect j. Nice. Well, let's see. If you take a refinement of a subdivision, do you get a better approximation of the integral or a worse one? Bad. Always bad. So that means the difference between either of the integrals and the lower or upper sums is less than or equal to the difference between the corresponding integral delta 0. But by assumption, those were less than the blue epsilon, which will eventually be epsilon divided by something. So if I could also show that the difference between S minus of FOL delta and S minus of FOL delta prime were less than epsilon, and S plus of FOL delta and FOL delta prime were less than epsilon, then I would have the result, right? Right, because if I wanted to know the distance between S minus of FOL delta and the integral, lower integral x of f dv, well, that's less than or equal to the difference between S minus of FOL delta and S minus of FOL delta prime, double. No, I want delta prime. There is no delta double prime right now. What upper bound do I have on that difference right now? Assuming that I can prove the thing that I said, that assuming I can prove it. Less than that blue epsilon. How big is the difference between S minus of FOL delta prime and the integral? There. Okay, cool. So what do I want to divide those epsilons by to make this actually work? 2, I guess. There are 2 of them. I'll remark that the red epsilon, I am not ready to say what that's going to be yet. So, if I can show these 2 inequalities, I'll be done. So let's try to show those 2 inequalities. Or maybe just one of them. Chances are if we can prove one, we can prove the other. Right. The difference between studying the soup and studying the int should be like the same. So, let's try to understand the difference between S minus of FOL delta and S minus of FOL delta prime. Who remembers the definition of the lower Darboux sum? It's the sum over all elements of the subdivision of let's draw a picture. But it's just going to be a one-dimensional picture, because that'll be good enough. So if I give you this interval, the interval from A to B, there's a function. I break this up into a bunch of pieces. S minus is supposed to be the sum that gives you the lower bound. So I guess it should be like how did I pick those rectangles? What's the height of each one of those rectangles?
Just the little m of that.
Yeah, it's the thing called little m, where little m is the inf of something. So it's m of f comma j. But then, of course, you have to multiply by the volume of j, and that picture would be the length of j, because one-dimensional volume is captured by length. Minus the sum of, oh, well, it's the exact same thing, right? And to get the upper sums, you study maxes. So I need to study like the difference between those. And here's where we'll remember that this delta prime is like the standard refinement of delta and delta 0. So let's suppose that j were in delta, and let's also suppose that there were an I in delta 0 with j contained in I. If j is contained in I, then what's the intersection of I and j? J. Hey, does that mean j is also an element of delta prime? So are there like some terms and no sums above that we can just cancel? Yeah, there are lots of them. Anything that's totally contained in one of the things in delta 0. So we can cancel some ends which correspond to j in the right-hand side of 1. Whenever j is a subset of one of the i's. So here's where it will become relevant how this stuff about building these I primes and I double primes. I claim this. For every element of the subdivision delta, one of the two things happens. Either there's an element in delta which contains that j, so I can cancel those ones, right? Or j is disjoint from every one of the I primes, which would then mean j is contained in x double prime. Does that make sense? Right, because x double prime is the union of all of the I double primes. And let's draw a picture of why before we actually give the proof. I'm going to go back to this picture. So in this case, the delta is like, well, it's functionally like that distance. How much you can expand the green set before you leave the black set. Well, let's consider one of these subdivisions j. So what do I know about j? I know that j is an element of a subdivision with mesh size less than delta. So I know that j has diameter less than delta. So let's suppose that one of those j's contained a point in that green ball. Well, that means that this point, the whole ball of radius delta centered at that point, is totally contained in that corresponding black set. But is everything in j contained in that ball? Any 2 points in j are going to be at most a delta apart. So it'll be contained in that ball, which is contained in the black set. So as soon as one of the j's contains a point in one of the green sets, one of the I primes, that j is totally contained in that I. Motivated by that, let's explain why this dichotomy happens, why one of these two things has to happen. So consider I want to prove something about absolutely every j. So let's consider any j in delta. If it happens to be that j intersect I prime is empty for absolutely every I in delta 0, then I'm already done, because B happens. I just wanted to show that A or B happens. So I get to suppose, without lots of generality, that for some I in delta 0, j intersect I prime is not equal to the empty set. Let's let P be a point in the intersection of j and I prime. P is a point in the intersection of j and I prime. let's use the fact that the diameter of J is less than or equal to delta I to conclude that J is totally contained in I. And now let's just focus on that. I think I have enough time to do that because it'll, I think, be a fairly straightforward containment proof. How do you show a set is contained in another set?
And then show it's in the other.
Pick point one, so it's in the other. Let's let, I don't know, P is one of the points, so I'll call it Q. It doesn't matter what you call this. Let Q be a point in J. Well, let's see, both P and Q are in the set J. So the distance from P to Q is less than or equal to the diameter of J. But that is now less than delta I. So I can definitely now conclude that Q is in something. It's in a ball. Well, that should be a capital I. So Q is in the ball centered at P of radius delta sub I. But wait, since Q is in I prime, I can use something here. Nope, since P is in I prime. Since P is in I prime, well, how did we pick these I primes? For any point in I prime, the ball centered at that point of radius delta is total delta I is totally contained in I. So, since this P is a point in I prime, the ball centered at P of radius delta I is contained in I, so Q is contained in I. How do I feel about that? That proof makes sense? That small argument makes sense? And again, my time management is bad. So, we're going to pick this up on Friday. There's only one homework problem for the course of this whole week. It's the one homework problem assigned today. And it will involve an imitation of this same argument that we're in the middle of, but for the computation of volume instead of integrals.